The objective of this experiment is to study the effect of an AC voltage on resistive, capacitive and inductive elements. We will apply an AC voltage, measure the current and the voltage across various elements to study their phase relationships. First of all, let us have a look at the basic theory of AC circuits. Here you can see a circuit, an AC is applied to a resistor, and below here you see the voltage waveform and also the current waveform. Both are in phase, that means they rise at the same time. When the voltage is rising, the current also is rising, and voltage is 0, current is also 0. In this side you are seeing the phasor diagram. So, in a resistive circuit, I mean resistor alone, the voltage and current are in phase. But if you take the case of an inductor, see an AC is applied to an inductor, here you can see the current is lagging behind. See, voltage is here and current is already here only. So, when the current is at 0, the voltage has already reached at the peak, that means it is ahead by 90 degree. So, current is lagging and voltage is ahead. So, this is the behavior of an inductor. And now we come to the capacitor. If you apply AC to a capacitor, you can see the current is ahead. See, when the voltage is 0, the current is already peaking here. So, here the current is leading in the case of a capacitor by 90 degrees. So, again here you can see the phasor diagram. See, voltage is here, but already the current has gone here 90 degree ahead. Now, in a general case, we are applying all the three in series. So, this is what we will study. We have AC applied to a resistor, a capacitor and an inductor in series. And if you see the phasor diagram, here is the voltage across the resistor, and this is the total voltage, and this is the voltage across the LC, that means inductor and the capacitor. And also you have to note that the voltage across the resistor always in phase with the current here. So, we will use this as our current, the voltage across our resistor. So, our objective is to perform this experiment and measure the voltages across various elements. We are going to perform this experiment using the Expeyes kit that has the sine wave generator and AC measurement terminals. So, we will use the sine output of this Expeyes kit, and we will use the A1, A2 that can measure and plot an AC voltage. We will be using some resistors, like here is a 1 kilo ohm resistor, and also we will use an inductor, that is a coil some 200 turns of copper wire and covered by some ferrite material, and also we will use some capacitors. So, these three elements we will be using with having different values. To make quick connections, we will be using some crocodile clips. So, first of all, let us make a connection from the sine terminal to A1, that is one of our voltage measurement point. And since we have to connect other things to A1, let us connect a crocodile clip to A1. So, these connections are done, and we will also make a connection to A2. So, our clip, these connections are made. Now, it is easy to connect the elements. First of all, let us have a look at this AC waveform. So, we have to start the program for that, and for this particular experiment, we will select a program from this menu, say study of AC circuits. The new window comes, and also you see the circuit diagram also is here. So, let us make our connections. A 1 kilo ohm resistor is connected to ground, and we connect a 1 microfarad capacitor. So, now if you look at the connections, the sine wave is directly coming to A1 and then it is going through the capacitor, and after the capacitor we are measuring here also the voltage we are measuring, and so if you look at the screen, there are 3 traces on the screen. The black trace is the applied voltage, the total voltage, and the red one is the voltage across the resistor, and the blue trace is the voltage across the capacitor. So, here you can see this voltage across the resistor, this red trace, its phase is same as of that of the current. We already told the across a resistor the phase of the voltage and the current are same. So, if you want to see the phase difference now, let us see the voltage across the capacitor. See the blue trace. See here it is 0 crossing, it is at 0, but already the current is at the peak. That means, you can see the voltage across the capacitor, the current is ahead, you can see that here, and the phase relation between the total voltage and the current is shown by here, this by the phasor diagram. And also you see here the observed values are plotted, the frequency is 147.4 hertz, total voltage is 3.61, and voltage across the resistor is 2.35, and voltage across the capacitor, we have not connected the inductor at the moment, is 2.7, and the phase shift is calculated value is 48 degree. And if you want to see the theoretical value of the phase shift, that can be done by using this calculator here. So, you have to enter the measured frequency, that is 147.4 hertz, and our resistance is 1 kilo ohm, but there is no inductor. So, make that as 0 and calculate the values. So, you can see here the capacitive reactance is 1079.7 and there is no inductive element, and the calculated theoretical value of the phase shift is 47.2 degree, and we are measuring here 48 degree. So, what we have done is now only the capacitor and the resistor in the circuit. Now, we will add the, or instead of the capacitor, let us try the effect of the inductor. So, we will replace the capacitor with the inductor now. So, we will take out the capacitor and bring the inductor in the picture. You can see inductor is connected, and now if you look at the phasor diagram, if you see here the current is now it is lagging, the voltage is, say this phase shift is around minus 3 degree, and earlier it was the current was leading, now the current is lagging, but it is not much because this inductance, the ratio between the capacitance and inductance is not quite high. So, now you can do the calculation, because this inductance is around 55 millihenry and there is no capacitance in the circuit. If you make the calculation, the calculated value is minus 2.9 and it is tallying very well with your measured value. So, this can be repeated with different values of inductors and capacitors, and you compare the theoretical value with the measured value. So, we have measured the phase shift using this device, and as well as the calculator allowed us to calculate the theoretical values, and these two can be compared. Now, we will use the same thing with both inductive and capacitive elements. So, let us make the connections. We will put both the inductor and the capacitor in the circuit and use another clip to join them here. So, now you can see here there is a resistor and the capacitor and the inductor. All the things are in the picture. Now, if you look at the screen, the net result is capacitive. You can see the current is ahead of voltage in the total voltage. And if you try to calculate the value, now let us put the capacitor 1 microfarad. It says the phase shift is 45.8 degree and our measured value is 46.5. So, these are well within the tolerance of the capacitance and the inductance used. Now, if you look at this diagram, you can find that if your capacitive reactance and the inductive reactance are equal, it will behave like a resistor. That means, this vector will move towards this and you will find that voltage and current in phase, and that means even though now across the capacitor we have the voltage, see at the moment 2.63 is there across the LC element, this blue trace, but you can adjust this value of this inductor and capacitance so that they resonate. That means, at resonance the voltage across this portion LC will go to 0. For that we will try to change the value of the capacitance and see whether we can obtain resonance. We will increase the capacitance from 1 microfarad to say 20 microfarad, and let us do the calculation first. With 20 microfarad, see this calculated value is phase shift is close to 0. So, let us replace this capacitor. We do not have a 20 microfarad capacitor. So, we will use two 10 microfarads, two of them in parallel. So, now we have in the circuit a 20 microfarad, and you can see here in the screen now the voltage and current are almost in phase. You can see the black and red traces are overlapping, and the voltage across this L and C, this portion is almost going to 0, the blue trace. The reason is now whatever the inductive part is getting cancelled out by the capacitor. So, that is how the resonance is observed. So, now we have seen how to use Expeyes to measure the effect of an AC voltage on resistive, capacitive and inductive elements.